Hello! In this video we will talk about the halting problem, Turing machines, and artificial neural networks, all visually summarized in a poster. Welcome to Marcharts. So, what is the halting problem? Let's have a look at the while loop in the C++ notation. You start with n equals 0, and while n is less than 5, you loop n++ command that adds 1 to n. Once the stopping condition is met, the program halts. On the other hand, if we remove the n++ line, the program loops forever as we will never meet the stopping condition. Deciding whether or not this program halts was easy. But can we do this for all programs? Before we can answer this question, we need to define the computational setup we work in. Here is a tape, a head that can read or write, or move to the left or to the right, and a finite state set and instructions. I'm a Turing machine. Except I'm not. This tape is finite. And for Turing machine, you need an infinite tape. I'm a linear bounded automaton, and for those, the halting problem is decidable. They either halt or repeat a state, G2-day finite memory. We are over here in the poster, but we need to generalize. We need a more powerful theoretical concept. We need a Turing machine with an infinite tape. This is where the halting problem lives. This is where we actually cannot decide for every program whether or not it halts for a given input. Let's see why. First, these programs must have their source code and inputs written using symbols from some finite alphabet. Let's count how many different strings we can make for every fixed string length n. Well, only a finite number. Now, we have an infinite tape, so we have an infinite number of possible string lengths. But this number is still countable. And countable union of finite sets is also countable. So there are only a countable number of all possible strings. Second, assume that there is a program H that actually decides for every possible source code P and an input X whether the corresponding program halts for the input. It gives 1 if the program with the source code P halts for the input X, and 0 otherwise. Now, because the number of strings is countable, we can arrange them as a sequence assigning each a natural number, 1, 2, and so on. Some of these strings can be a valid source code P, others can be inputs X, and what is important here, a string can be both a source code and an input. In turn, we can arrange all the outputs of the program H into a nice table. And whenever you see a table like this, the famous diagonal argument due to Cantor applies. Construct a new program, let's call it source code P star, that loops for its input X if H gives 1 on the diagonal of this table, and halts for its input X if H gives 0. If this table exists, this program is well defined. The problem is that this program source code cannot possibly be on any row of the table. It is not the first program, since H gives for this source code and the same input 0, so the program with such a source code and input is supposed to loop, but by our definition P star halts. It is not the second program, since H gives for this source code and the same input 1, so the program with such a source code and input is supposed to halt, but by our definition P star loops. And so on. Simply, P star is designed in a way that it cannot be any of the source codes in the table. It is important to realize that our assumptions allow us to construct this contradiction. We do not get it for free. For example, this argument would not work if the tape were finite or uncountable. That assumption is the key to the proof. A possible example of a program that we might never know whether it holds for every input is the Collatz conjecture. We know that for many inputs this, what is simply a while loop, holds, but we do not yet have a proof that it holds for all inputs. An interesting puzzle is how the artificial neural networks relate to Turing machines. As a computational concept, they are very different. They are inspired by our brains. They work with real numbers, which act as weight between neurons. And since these real numbers are uncountable, they cannot be Turing machines with their countable tapes. Finally, our real computers, with their finite memory, are neither. We can only approximate these theoretical concepts using our real machines. A thesis could be then proposed. If our brains can actually work with real numbers as in the theoretical model, then we are something more than any machines we will ever make. Best wishes from Marchard!